We continue with our first talk on the contributed paper, which is Interpolation and Quantifiers in Ortholattices, and will be presented by Sankalp Gambhir.
Well, thanks for the introduction. This is joint work with Simo and my advisor, Viktor Kunčak, both of whom you can find in the audience. So there's a lot of stuff in the title, and this begins with the fact that we rely and care about very extensively about propositional reasoning, be it for model checking or other applications. But in general, it's quite a hard thing. It means that our systems, in the end, struggle with scaling to very large applications. The validity problem, in particular, is co-NP hard. And the question becomes, can we do better? So we want to look at abstractions of this kind of reasoning. We want to look at weaker forms of reasoning such that the reasoning is still correct. We maybe don't catch everything we need to, but we still get good answers fast. We need our reasoning to be sound. We never want an incorrect answer. And we want this reasoning to be predictable and, of course, efficient. And since we're looking for predictability, we suggest, okay, maybe it's good to start looking at algebraic subsets, things that you can have very nice mathematical characterizations for and still reason about them well. So one such candidate is intuitionistic logic, which has been studied for a very long time. But unfortunately, the validity problem is p-space complete. So that doesn't help. So as an alternative, we study something called orthologic, for which the validity problem is known to be quadratic-time, while still having a nice algebraic characterization. And in the same way that Boolean algebras correspond to propositional logic and Heyting algebras correspond to intuitionistic logic, the models of orthologic are ortholattices, which appear in the title. So these ortholattices are characterized by starting with the familiar laws for Boolean algebras, containing the usual operators of conjunction, disjunction, and negation, the laws of commutativity, associativity, constants, double negation, De Morgan's laws, and taking the last law of distributivity and replacing it with a slightly weaker degenerate version. And this is what allows you to avoid the large state space explosion and have this quadratic time validity checking and normalization. So this gives you this incomplete but still sound approximation for Boolean algebras. And you not only have validity checking, but a complete normalization procedure. Recently, we found use for this in a formula caching for a program verifier, wherein the formulas are normalized before caching. And you can also use the normalization procedure to check for implication between formulas also in quadratic time. And we've also implemented it in our interactive theorem prover, where we use it for small manipulations of formulas for human interaction. And this gives quite a large speed up, where you only need small manipulations in the middle of proofs. For this paper, we'll be interested in the question of interpolation. And to get there, first we try to look at it through the perspective of quantifier elimination, for which we first look at a proof system for a quantified orthologic. We talk about then the failure of quantifier elimination within this logic. Then we discuss two notions of interpolation, the first based on refutation proofs, which fails to exist here. And then finally a notion of interpolation, which is perhaps more general in the case of these non-Boolean lattices based on implication. So since we care about interpolation, we're going to be working with proofs, which will be written in the form of a sequent calculus. As a small reminder, we write a sequence as an ordered pair of sets of formulas. On the left, you have a set of formulas which are the assumptions of your proposition. On the right, you have a set of formulas which are your conclusions. And the whole thing written from left to right becomes a proposition. And we write our proof rules as a fraction, with the bottom being a single conclusion and the top being 0 or more premises of the proof rule. In the same way that intuitionistic logic has been classically known to correspond to taking propositional logic and restricting it to always have only one formula on the right-hand side, orthologic is known to have this characterization of having at most two formulas in the entire sequence at any point. This can mean one formula on the left, one on the right, two on the right, two on the left, or less. It becomes convenient in ortholattices to write your formulas, your sequence not in the classical notation, but with formulas with a left and right annotation on the top. So orthologic is characterized by the familiar proof rules for classical propositional calculus, only with this added restriction of having at most two formulas in the sequence at once. So this proof system, following normalization procedure, allows you to have proof search which is also quadratic in the size of the formula. And even when you add axioms, which is by itself a non-trivial result, you still have cubic time proof search. And this leads to several other interesting results, which you can hear about in my co-author's talk later this week at Popple. So we care about here the question of interpolation, where we ask, given two formulas A and B, such that you have a proof that A implies B, can you find a formula I such that A alone implies I and I alone implies B, where I only shares the free variables of A and B, here being Y? And we care about this because in the context of model checking, this allows you to focus your search to relevant facts, avoiding some space explosion. It allows you to report better counterexamples to users by removing extraneous information, and it generally assists in abstraction, generalization, and refinement. And in the case of Boolean algebras, you get some interpolants for free by simply quantifying away all extraneous variables. With some effort, you can show that these are indeed interpolants. And because Boolean algebras admit what is called quantifier elimination, you can find formulas equivalent to the quantified ones, which do not contain any quantifiers. And these serve as the nice quantifier-free interpolants that we are looking for. So if we could do the same thing for ortholattices, that would be quite nice. So to this end, we start looking at quantifier elimination. And in fact, this would give us not only these some interpolants, if they would give us least and most general interpolants. And in general, this can also allow you to do symbolic state computation based on quantifier elimination. But orthologic currently does not have quantifiers. So first, we start by giving semantics for quantified orthologic on complete ortholattices. To do this, we add two operators, the greatest lower bound corresponding to universal quantification and the least upper bound corresponding to existential quantification. And this is done over complete ortholattices to ensure that the lower and upper bounds actually exist. And we add the relevant rules for introducing quantifiers on the left and right hand side of the sequence, which are the same as you'd find in propositional logic. And we show that the proof system we introduce is both sound and complete for complete ortholattices, which is to say that when you have inequalities, they correspond directly to sequence. If you can prove any inequality gamma less than equal to delta with respect to the laws of ortholattices, then the corresponding sequent with gamma on the left hand side and delta on the right hand side is provable within this system. So we consider the question of quantifier elimination, which is given a formula phi that contains some quantifiers. Can we effectively produce an equivalent quantifier free formula, QE of phi, that contains no quantifiers? And we show that quantified orthologic does not admit quantifier elimination. We show this by counterexample. This formula phi contains only y as a free variable. And so whatever quantifier eliminated version it has must only contain y as a free variable as well. And we choose the following two models, the ortholattices M2 and M4. And we show that any formula which contains only y as a free variable cannot evaluate to the same value as phi in both of these models simultaneously. The lattice M2 on the left hand side satisfies distributivity and is thus a Boolean algebra. And this becomes a differentiating factor between the two models. So given the fact that orthologic does not admit quantifier elimination, the question of interpolation becomes more interesting. And in fact, in general, it's more common to get interpolants, even in the classical case, out of unsat proofs rather than directly through quantifier elimination. So instead, we consider this notion of interpolation based on refutation proofs, wherein we ask, if you have given any two sequence gamma and delta, a proof of contradiction or the empty sequent assuming them, can you find an interpolating sequent I such that you can deduce I from one of the sequence, say gamma alone, and I and delta are inconsistent, there's a proof of contradiction assuming them together. And once again, I contains only the free variables of gamma and delta. This is something that is quite natural that we might want to do for model checking, for example. But unfortunately, orthologic also does not admit this notion of interpolation based on refutation. Once again, we have a counterexample of these two sequents. The only common variable between these is y, and we show that any sequent I containing only y as a free variable, similar to the quantifier elimination example, cannot be a refutation-based interpolant. Finally, we consider this notion of interpolation based on implications, which is perhaps a bit more natural in non-Boolean lattices, which says given two ortholattice formulas gamma and delta, if you can prove gamma is less than or equal to delta, then you should be then can you find an interpolating formula I such that gamma is less than I is less than delta, and I contains only the free variables of gamma and delta. Note that if you're working inside a Boolean algebra or propositional logic, these two notions of interpolation are actually completely equivalent. But when you lose distributivity, these two notions become differentiated. As we will see, because while working with proofs, we first generalize the statement to work with sequence. So we say, given a provable sequent gamma delta, an interpolant is a formula I such that you can prove gamma with I on the right hand side and delta with I on the left hand side, and I once again contains only the free variables of gamma and delta. And we show that orthologic does admit this notion of interpolation based on implications, unlike the refutation case. And the proof proceeds by induction on the proof of the sequent gamma delta, and thus the interpolant computation is linear time in the size of the proof. And because of this quadratic time property of quadratic size property of orthologic, you can actually find the interpolant in quadratic time in the size of the formula itself. So as a quick overview of the proof, as a base case, you only have the hypothesis rule, which has no premises. And here the interpolant is trivially the hypothesis formula phi itself. And then you have the inductive case, which has to be done for each of the proof rules. As an example, we have here left hand. The inductive hypothesis says that you have an interpolant C for the premises gamma phi L, such that there are proofs of gamma with C on the right hand side and phi with C on the left hand side. And for the inductive proof, we extend these proofs to show that C is also an interpolant for the conclusion. On the left hand side, the proof is trivial, and on the right hand side, we simply have to apply the left hand rule as well. This can be repeated with some variation for each of the different proof rules to complete the induction. So starting with orthologic, which as I mentioned is an incomplete but sound weakening of classical propositional logic, we have a sound and complete proof system that works in a quadratic time and size of the formula. We showed semantics of quantified orthologic, the absence of quantifier elimination within this new logic, and the absence of this notion of interpolation based on refutation, and the existence of a somewhat natural notion based on implications inside the lattice. With some recent use that we've seen for ortholattices in case of interactive theorem proving and in verification, we hope that this interpolation result will lead to more interesting uses of ortholattices in model checking as well. Thank you. Any questions?
In your last remark, you distinguish between interactive theorem proving and verification. What did you mean by that? What is the distinction?
Oh, okay. So that was basically based on how we have managed to use it in the past. In the case of interactive theorem proving, we provide it explicitly as a proof step where you can perform formula rewrites based on what you're able to prove within ortholattices. While in verification, we mostly use it for caching and normalization, aggressive normalization for automation. While for interactive theorem proving, we use it for allowing humans to do fast manipulations of formulas, because those happen quite often, and so you don't want to call a SAT solver every single time you have a proof step like that. So we use them in completely different ways in these two scenarios. So I don't mean to differentiate between the two applications, but in how we've used them up to this point.
Hey, so you say that you have several kinds of interpolants that are different in this logic, and which of them is the one that you want to use in the application in model checking?
The one that we managed to prove exists up to this point. The one based on refutation would have been pretty nice, but currently those don't seem to exist. It would be also interesting to consider in the future whether we can find interpolants in the presence of quantifiers or axioms, which we currently don't know.
But would it mean something different for the verification? Like, would you actually need an interpolant for something? You get something a bit different in this logic. So.
I think so, yes, because unlike the Boolean algebra case, the less than equal to does not directly correspond to implication. they mean slightly different things, and some things which you can prove, for some things you can prove A less than equal to B, while for some things the probability might be, probability by assuming as axioms is sometimes stronger, yes. So unlike the Boolean case, they don't completely correspond to each other.
Any further questions? But I have a question. I mean, it's maybe a follow-up question to that regarding the use of model checking and so on. So you mentioned caching. So does the interpolation in some way help with caching, right? Can you kind of generate, like, somehow have more general cached results based on that?
Okay, we have not attempted that yet. That's interesting future work. The caching result is from last year. We have not extended it with the interpolation technique yet. This is something that we would like to try, yes, but we don't have results yet.
Okay, thanks. Any further questions? If not, then let's thank the speaker again.